Okay, today I'm going to be going over the three old men hypothesis, or not really hypothesis. I guess hypothesis is the wrong word. I'll change that out eventually. So basically, in my math class, we're doing discrete math and that kind of thing. And so we got a question, and it goes like this. Three old men get a bacterial infection. There's a 10% chance that one will die upon infection. So for one, if you're looking at just one of these old men, there's a 10% chance that he will die from that bacterial infection. And so all three of these men get the infection. What are the chances that only one of the men will die? So one out of the three men dies. What are the chances that that will happen? And well, if you do the math over here, the probability that total dead is equal to 1 is equal to 10% times 9%, so 90%. So 90% is the chances that he lives times 90%. So one of them died, two of them lived. Plus one died, one lived, one died, plus one died, or one lived, one lived, one died. So you do all that together and it comes out as exactly 0.243 or 24.3%. So mathematically there's a 24.3% chance that only one of them dies. Now, when I was at school, my math teacher, he said we would need a computer simulation to, figure it out. Or I don't remember exactly what he said, but he said something about a computer simulation, and that immediately got me thinking. I know how to code in Java. I might as well give it a shot. So right then and there, I pulled up my laptop and I started working on this program. And there was a problem. There's a big problem. Um, I would run the simulation more than 100,000 times for each pass, and it would come out with the answer 0.25. It would be 25% or above. It would be 25.3%. 25.8% was the highest one that I ever recorded. And that's quite a lot further away from 24.3% than you would expect for 100,000 passes. So I came here back onto my home computer and time to do some calculations. This computer is a whole lot faster, so I can actually do well over 1,000,000 passes if I wanted to, and it wouldn't take nearly as much time as it did to do 100,000 on the laptop. So I'm just going to be running through the program real quick, see if I find any errors. We're going to correct those errors if we find any, and then we're going to do a couple runs and mark down what we find. So first, establishing the three old men. They are established as Boolean variables. So the Boolean status determines if they died or not. So false means they didn't die, true means they have died. These are the individual variables. So random, that's going to be our randomizer. One of the differences between the old program and this program is that the old one randomized between 0 and 100 to get the chances. So if it was between 0 and 10, it would be a death, or if it was between 11 and 100, it would be alive. But this one instead works with double and randomizes up to 100,000 instead of byte before. So anything below 10,000, so even 99,999.999 repeating up to a certain point will be a death. So this one is I guess you could say a lot more random, which is an interesting phrase, more random. But then we have total dead and total live. These are basically going to be used for taking care of how many have died and how many have lived. So we can find out in this trial how has it only been one that died. And so if it's only one that dies, that fills our conditions. These are for finding the percentage, so total true observations, total false observations, and total trials. So basically this we'll get there later, and then the percentage. So this is a for loop, which means it'll just do it a whole bunch of times. So establishing it as 0, once it hits 1,000,000, it will stop, and each time it finishes, it will try it again and increase that number until it gets to 1 million. And so this is basically how it works. You randomize a number between 0 and 100,000. If it's under 10,000, he's dead. Total dead goes up, and it'll say he died. Otherwise, total live goes up. And it'll do that 3 times, one for each old man. If the total, here, that's actually wrong. So I did find a problem. If total dead is 1, then the total number of true observations will increase. So if only one and only one of the men has died, that is considered a true observation. It fulfills our requirements for a true observation. Otherwise, it'll be false. After all that is done, it will affirm that we have completed a trial run or completed a pass, and total trials will increase by 1. And then we reset all the variables for the next run, for the next pass. And then this is just the percentage calculation here. So the total number of true observations divided by the total number of trials. And then it'll print out total number of true, total number of false, total number of trials, and then the percentage of those that came up as true. So this is a slightly improved system to the one that I had on the laptop. It's a much faster calculation. I'm not entirely versed on how math.random works in Java. I'm pretty sure it takes from the time, the computer time, either that or the CPU clock. So maybe that might have something to do with it, because this is a much faster CPU. Who knows? It could be a number of things that fixed it, which is very unscientific of me to, test like 3 different things that could have gone wrong at once. I probably should have done them each individually to find out, but I just want to, this is just something I'm doing for fun. It's not really that important. So we're going to save and we're going to run it, and then I've got a notepad. I'm going to write down the results that we get on here. So pass 1, pass 2. I can actually, let's see, do this. Pass 2, 3, 4, 5, 6, 7, 8, 9, 10. Or well, let's say 9. And then we'll make a pass 0 at the beginning just because it looks a little neater. All right. So I'm gonna write all these down once we go through them. So it's going to simulate. It's going to do this operation of randomizing the live or die chance 1,000,000 times, and then it will come out with a percentage down here. This is a wrong one because it was wrong earlier, but we've fixed it. And let's give it a shot. So you can see down here in the console, it's going through quite a lot of these different calculations here. It'll take a little while, maybe a minute, for it to go through 1,000,000. And just like that, would you look at that? So it appears that my guess would be that the randomizing system in this one is a whole lot better. So I can actually get rid of this problem here. So for our first pass, we got a nearly perfect percentage of 0.243, also known as 24.3%. Or well, 243,561. 24.3561%. That, I would say, falls within our range. Obviously, this is an amateur operation. If this was some professional science thing, I'd be using a supercomputer and doing 1 trillion simulations, but unfortunately I do not have the time nor the resources for that. So anything within 1 of 24 point anything within 0.1 of 24.3 is acceptable. So we're going to, let's actually make this look real nice. If I get this one, bang, check. That one has, or we can actually put it at the end. That one has passed. Pass 0 has fulfilled our test. And we're going to do this another 9 times, and I'll get back to you then with the results. All right. So all of the passes have finished. I've done 10 passes of a million different tries of the of each individual test of 3 old men with 10% chance of dying each. the averages have come out at 24.29749% with a differential of 0.00361. So that even falls under to standard avvikelser, they call it in Swedish. So yeah, confirmed.